Good morning, students. In today's lecture, I'll be discussing about CPU scheduling algorithms. CPU scheduler, which is one of the components of the operating system, addresses the problem of deciding which of the processes among the processes which are there in the ready queue will get CPU first to run. There are several CPU scheduling algorithms. First come, first served scheduling, shortest job first scheduling, round robin scheduling, priority scheduling, multi-level scheduling. See, we will be discussing about all these algorithms. When it comes to um, operating systems which are popular like Windows and Linux, they may not use one single scheduling mechanism in total. They use combination of these scheduling algorithms. Let me first take up first come first served scheduling algorithm and let us discuss about this algorithm in detail. First come first served scheduling algorithm is the simplest of all the other algorithms. Here, whichever process makes the request for CPU first will get the CPU first. Let us try to understand this in detail. This first come first served scheduling could be realized with the help of a data structure called FIFO queue. I'm sure that all of you are aware of what is a FIFO queue. Let us assume that we have two pointers, front and rear, initially pointing to null because there is nothing in this queue, FIFO queue. Now if a process, let's say P0, makes the request for getting the CPU, the PCB of this process P0 or a pointer to the PCB of this process P0 is placed at the rear end of this queue. So that means both F and R would be pointing to PCB of P0. Similarly, next request comes from, let's say, process P1. So this pointer, let me erase this rear pointer, okay, will now start pointing to P1 in the sense that pointer to the PCB of P1 is placed here. So similarly, this queue grows. Now, when we have to make a decision of which process, this is a ready queue, which process will get the CPU first, it is very simple. Whichever process is at the head of this queue will get the CPU. So in this case, process P0 will get the CPU first. Once process P0 finishes its CPU burst and goes into wait queue, P1 is taken up for execution. So this is what is first come first served scheduling. This is a we have discussed about the difference between preemptive and non-preemptive CPU scheduling. This is a non-preemptive CPU scheduling because once the process gets the CPU, it goes on till it completes the CPU burst. Therefore, it is a non-preemptive algorithm. Hope you have understood what is first come first served scheduling algorithm. Let us try to understand this algorithm clearly with an example. Um, Let me take this example. In this example, I have assumed that three processes come into the ready queue in this order, all at time 0. That means all these processes come into the ready queue at the same time, more or less at the same time, but in this order: P1, P2 and P3. Now these three processes are present in the ready queue, and each process I have attached a burst time, CPU burst time, with every process. Here you know that every process will have multiple CPU burst time and multiple IO burst times. For simplicity, or to understand this algorithm better, we have taken only one, we have associated only one CPU burst time with all these processes. So P1 needs 24 time units to complete its execution, or to complete its CPU burst time, to be specific. P2 needs 3 time units to complete its CPU burst time, and P3 needs 3 units to time units to complete its CPU burst time. Now let us try to represent the the scheduling decisions made by FCFS algorithm with the help of a Gantt chart. So what is FCFS scheduling algorithm? It selects the process um, in the order of its request for allotting the CPU. So this P1 is present at the front of the ready queue, so therefore the P1 is selected first to run on the CPU. So therefore, what is the time that it is going to spend in the ready queue to get the CPU? It is equal to 0, because it has arrived at 0, and this is the first process which is making request for CPU. Therefore it is immediately given the CPU. So I have put a rectangle here and written P1, and its execution starts at time t is equal to 0, and it runs for 24 time units. Because it is a non-preemptive algorithm, no other process will affect its execution, or this process is not removed from the CPU once the CPU is allocated to it. So that means the P2, which has made the request for CPU, it is next to P1. So after P1 completes its entire CPU bus time, P2 is given CPU. So that means this P2 starts its execution at t is equal to 24, right? Though it has come at time t is equal to 0, but it has made request just after the process P1. Now this P2 will run, what is the time unit amount of time it requires to complete its CPU burst? 3 time units. So it is going to run till 27. After that P3 gets CPU, and P3 is going to run for another 3 units and complete its CPU burst. Okay, now this Gantt chart clearly tells us how these processes are selected from the ready queue and they are run. P1, because P1 has made the request for CPU first, and it is at the front of the ready queue, and ready queue is nothing but a simple FIFO data structure. P1 is picked up first for the execution and it is given CPU. So P1 runs for 24 time units. Once it completes its CPU bus time, P2 is selected and it will run for another 3 units, and then P3 is selected. So that is shown with the help of this Gantt chart. Now let us calculate the waiting time. Let me write this as WT, waiting time of each of these processes. P1 has arrived into the ready queue at 0. and immediately gets CPU. So therefore, it waits for 0 time units. Whereas this P2, uh, though it comes at t is equal to 0 into the ready queue, it will get the CPU only at 24. So that means it has to wait for 24 time units to get the CPU. Similarly, P3, it also comes into the ready queue at more or less at t is equal to 0, but it is making the request for CPU after this P2. We have taken it that way. It is the last process which is there in the ready queue, so it is selected for execution on CPU after P2 completes. So this P3 will start its execution at 27. P3 will wait for 27 time units. So that we have considered now, that is 3, that is equal to 17. If you take the unit of time as milliseconds, then it is going to be 17 milliseconds. Now, whichever scheduling algorithm minimizes this average waiting time is a good algorithm, or it's a better algorithm. Now let's try to compute finishing time or completion time. In completion time, you can simply look at this Gantt chart and write the completion time. What is the completion time of P1? It is 24. So simply write 24 here. What is the completion time of P2? P2 completes at 27. So simply write 27. What is the completion time of P3? P3 completes at 30. So simply write the completion time as 30. Now from this you can calculate the turnaround time. Turnaround time could be calculated in two different ways. Now let's use this formula: completion time minus the arrival time, or the finishing time minus the arrival time of the process. Now P1 completes at 24, but it arrives into the queue, ready queue, at time is equal to 0. Therefore the turnaround time is 24. Only if the arrival time changes, this turnaround time will change, otherwise it will be same as the finishing time. So similarly for P2 also, it is 27 minus 0, because all of them, we have assumed that all these processes arrives into the ready queue at 0. So therefore this is also is equal to 27, and the turnaround time of P3 is also is equal to 30. Okay, so now we have got for this algorithm, we have got the average waiting time and we have got the turnaround time. Now these values could be used to compare the performance of HCFC scheduling with other scheduling algorithms. Now let us take another example. In this example, you see, along with the burst time, we have considered different arrival times for different processes. Just because I write P1 as an identification for a process, it doesn't mean that P1 should arrive into the ready queue first. So if you see this case, P3 is the one which comes into the ready queue first, because its arrival time is 0. After this, P2 is the one which arrives into the ready queue, and after that P1 is the process which arrives into the ready queue. Now if you look at the FIFO queue structure, now the PCB, the first head or the front pointer is going to point to the PCB of what? PCB of P3. The next location will have what? It will have the pointer to the PCB of P2, because P2 has come into the ready queue after P3. And similarly here we will find the pointer to the PCB of P1, and rear pointer will be pointing to this. This is how ready queue looks like. Okay, now when let me try to write the Gantt chart for this. This Gantt chart is going to show us the scheduling decisions made by the FCFS scheduler. Now at time is equal to 0, there is only one process in the ready queue, that is P3. So therefore CPU is allotted to P3. P3 is going to run for how many time units? Its burst time is 7. So therefore it is going to run for 7 time units and complete after 7 time units. At that point of time, both these processes have come into the ready queue. But if we look at the ready queue, P3 has already gone out of the ready queue. Now, which is at the front? Now, the P2 is at the front of the ready queue. So therefore, now P2 is given the CPU. The execution of P2 starts at 7 and it is going to run for 6 time units. So that means P2 will complete its execution at time t is equal to 13. And after this, now this P2 will also go out of the ready queue. The only process which is left in the ready queue is P1. P1 is given CPU at time t is equal to 13 and P1 is going to run for 10 time units. So this is going to finish at t is equal to 23. Okay, P1 is going to finish at t is equal to 23. Now this is the Gantt chart. Now let us try to calculate the waiting time, completion time and turnaround time. What is the waiting time of process P1? P1 arrives into the ready queue at a time is equal to 2, okay, and gets CPU at time 13. So therefore its waiting time is 13 minus 2, that is equal to 11. What is the waiting time of P2? P2 arrives into the ready queue at time t is equal to 1 and gets CPU at what time? 7. So therefore it is equal to 7 minus 1, that is 6 time units. And what is the waiting time of P3? P3 comes into the ready queue at time t is equal to 0 and immediately gets the CPU. So therefore its waiting time is equal to 0. I hope you understood this. Now let us write the completion time. P1 completes after 23 time units. You simply look at the Gantt chart and write P2 completes after 13 time units and P3 completes after 7 time units. Right? Now you will have to calculate the turnaround time. Completion time of P1 is 23, but it arrived into the queue at t is equal to 2. So therefore its turnaround time is equal to 21. How you can cross verify this? You can add the waiting time of this process to the burst time of this process. You will get the same value. Here what we have done, we have subtracted the arrival time from the completion time or the finishing time. Both will give us the same value. So what is the waiting time of P1? Waiting time of P1 is 11. Burst time is 10. If you add, you will get 21. Similarly, what is the turnaround time of P2? Completion time is 13 and what is its arrival time? That is 1. So therefore, its turnaround time is 12. And what is the turnaround time for P3? Completion time is 7 and its arrival time is 0. 7 minus 0 will give us the turnaround time for process P3. So you can also calculate one more parameter which will be useful, that is average waiting time. In this case, average waiting time is equal to 11 plus 6 plus 0, that is 17, divided by 3 processes. That will be the average waiting time for this scenario. Okay. Hope you have understood this clearly, and this kind of problems will appear in the university examination. So you should be in a position to solve such problems. Now let us move on and look at some of the issues associated with first come first serve scheduling. Okay, let's take this example. Here I have taken three processes, P0, P1 and P2. I have taken one CPU burst of all these processes and also one IO burst of all these processes. Now if you look at it carefully, as we discussed in the previous lecture, P0 is clearly a CPU bound process, whereas P1 and P2 are IO bound processes. Now what happens, assume that now the P0 has come into the ready queue first and got the CPU and it is running. Now what is there in the ready queue? Now pointer to the PCB of P1 and pointer to the PCB of P2, and we are assuming that they have come into the ready queue in this order. Okay. Now this P1 and P2 are waiting. When these are waiting, our IO devices, now the P1 and P2 and P0, all these are supposed to do some IO operations in this IO burst. But because the P0 is on the CPU, it's a process having long CPU burst and it has occupied the CPU. P0 has occupied the CPU. So therefore, all the IO devices are going to remain idle. Okay, this is ready queue. After some time, what may happen? You look at the waiting queue. Let us assume that P0 completes its execution on CPU, or it completes its CPU burst and enters into wait queue. P1 and P2 also quickly completes because they are IO bound processes and having very small CPU burst times, so they can quickly complete and come to the waiting queue. Let's assume that this waiting queue appears like this. Now all of them are doing what? All of them are waiting for some IO operations to happen. What has happened to the CPU now? Now CPU will become idle. Right? So what the point that I am trying to make here is that the resources are not effectively utilized. Now we told you in the beginning that the scheduling algorithm must be designed in such a way that the resources are utilized properly or effectively. Now in this case, resources are not effectively utilized. Why is it happening? It is because one big process, that is P0, having long CPU burst, is scheduled ahead of small processes, that in the sense that the processes having small CPU burst time. So this is called as convoy effect. There is something like this. There are cars which are capable of going at the rate of, let us say, 120 kilometers per hour. But because this big truck which is going ahead of these cars and it is going slowly, these are supposed to wait. All these cars are supposed to wait. So that means we are underutilizing the capacity of these cars. So this picture shows us gives us a clear understanding of what is the convoy effect. So let me put that in words. Convoy effect is nothing but if a process having long CPU bus time is selected to run on the CPU ahead of other shorter processes, the shorter processes will wait for that one big process to get up the CPU. So this results, as I discussed in the previous slide, this results in lower CPU and IO devices utilization. So this effect is called convoy effect. That's the problem associated with FCS. Another problem which is associated with FCFS is this is not suitable for time sharing system because it is a non-preemptive approach. So therefore, once a process gets the CPU, it will not leave the CPU until it completes its CPU burst. So therefore, this kind of algorithm is not suitable for time sharing systems. So these are the disadvantages. Now let's see how these disadvantages are overcome in the other scheduling algorithms that we are going to discuss after this. Let us now discuss about another scheduling approach, which is shortest job first scheduling. In this case, as and when the process arrives into the ready queue, the process gets its next CPU bus time attached to it. Okay, and when the CPU is available, among the processes which are there in the ready queue, whichever process has got uh, smallest next CPU burst is selected for execution or is given CPU. Suppose if let us assume that there are two processes having the same next CPU burst time. In this case, how to break the tie? That is when the operating system can use HCFS, and whichever process has come into the ready queue or made the request first for the CPU can be taken up for execution. Now let us take the same example which we took to understand the first come first served scheduling algorithm. So here I have assumed that there are three processes in the ready queue and all of them have come at time t is equal to 0. We have uh, next CPU bus time attached to all these processes. P1's next CPU bus time is 24, P2's next CPU bus time is 3, and P3's next CPU bus time is 3. Now, according to shortest job first scheduling algorithm, let us try to write the Gantt chart which represents how scheduling decisions are made by this algorithm. At time t is equal to 0, all these processes are there in the ready queue, but there are two processes P2 and P3 having same CPU bus time and less than the CPU bus time of the P1. So therefore, the scheduling algorithm can select either P2 or P3. So there is a tie between process P2 and P3. So what can be done? A P2 has made the request for CPU first and then the P3. So therefore P2 can be given CPU first. P2 will start its execution at t is equal to 0 and it continues to execute till its CPU burst is over. That is, it stops at t is equal to 3. Now P3 can be picked up for execution. Now P3 will run till time unit 6. After that, P1 can be given the CPU, and P1 will completes its CPU burst, that is 24 time units, and finishes at time t is equal to 30. Now, if you recall, all these processes completes after 30 time units, which is same as that of FCFS. In FCFS also 30 time units are required to complete the execution of these three processes. Here also same amount of time is taken, but when you calculate the average waiting time, you would know the difference between FCFS and shortest job first scheduling algorithm. Now let us do that. Let us calculate the waiting time for P1. Now P1 comes into the ready queue at t is equal to 0, but it gets CPU at t is equal to 6. So therefore the waiting time of P1 is equal to 6. What is the waiting time of P2? P2 immediately after it comes into the ready queue, it gets a CPU, therefore it doesn't wait. So its waiting time is equal to 0. P3 will wait for 3 time units. So therefore its waiting time is equal to 3. Now add all this and divide it by number of processes, we get average waiting time. That is equal to 3. Now if you take the unit of time as milliseconds, it is equal to 3 milliseconds. Whereas in case of FCFS, this was 17 milliseconds. What would have happened in case of FCFS? Because P1 is making the request for CPU first, P1 would have got the CPU first, then P2, and then P3. What is the change here in shortest job first scheduling algorithm? No, it compares the next CPU burst time of all these processes. P2 and P3 has got the minimum or less. Unfortunately, in this case same, therefore it uses FCFS to break the tie and selects P2 because it has made the request for CPU before P3, and P2 is given the CPU first, after that P3, then P1. So this is how the scheduling happens in shortest job first scheduling algorithm. Now let us try to compute the finishing time or the completion time. What is the finishing time of P1? P1 completes after 30 time units, P2 completes after 3 time units, and P3 completes after 3 time units. So in this case, the arrival time of all these processes is equal to 0. Therefore, the turnaround time will be same as that of the finishing time. Shortest job first scheduling algorithm can be non-preemptive or it can be preemptive. So let us try to understand the difference between non-preemptive SJF and preemptive SJF. Okay, so let us take this example. Here again, I have not considered the arrival time, and I have assumed that all the processes have come into the ready queue at the same time or at t is equal to 0. Okay, and the next burst CPU burst time of all these processes are given here. In case of a non-preemptive SJF, what happens? Which one is picked up first? If you see, this P4 has got smaller next CPU burst time, so therefore this is picked up first. Let us try to write the Gantt chart. At the time t is equal to 0, which process is picked up for execution, or which process is given the CPU? It is P4. So P4 runs for 3 time units, and then among the remaining processes, now this P4 is done, among the remaining three processors which has got the shortest next CPU bus time, that is this P1. So therefore P1 is given CPU after P4 and P1 completes after 9 time units. So now how many processes are left out? Now P2 and P3 are left out. Among these two processors, process P3 has got a less next CPU bus time. So therefore P3 is selected for running, or P3 is given CPU, and P3, since it is a non-preemptive scheduling algorithm, P3 would compute its CPU burst. So that means it is going to complete after 16 time units. Then P2 is given CPU and P2 is going to complete after 24 time units. This is how the scheduling happens in case of shortest job first scheduling. It is a non-preemptive scheduling. So that means once the CPU is given to a process, up till the process completes its CPU burst, a process is not taken out of the CPU. So that's a non-preemptive scheduling approach. Now let us calculate the waiting time and turnaround time. I have not written completion time or finishing time because all of them have arrived at t is equal to 0. Therefore this turnaround time and finishing time would be same. Let us calculate the waiting time and also calculate the average waiting time. What is the waiting time of P1? P1 has arrived into ready queue at t is equal to 0, but P1 has got CPU after 3 time units, so its waiting time is 3. Similarly, what is the waiting time of P2? Waiting time of P2 is 16 time units. Okay, waiting time of P3 is 9 time units, and P4 is the shortest job in this case, so therefore its waiting time is 0. So what is the turnaround time? Um, Turnaround time is nothing but the completion time minus the arrival time. What is the completion time of P1? P1 completes after 9 time units and its arrival time is equal to 0. What is the completion time or turnaround time of P2? P2 completes after 24 time units. You can also take this as, like I said, it has waiting time plus the burst time. That will also give you the turnaround time. What is the waiting time of P2? It is 16, burst time is 8, so therefore it is 24. Okay, similarly for P3 it is 16 and for P4 it is 3. So this is how we can calculate the waiting time and turnaround time. You can calculate the average waiting time. How much is that in this case? It is 16 plus 9, 25, 25 plus 3 is 28. 28, this time we have 4 processors, so therefore it is equal to 28 divided by 4. So it is 7 time units, could be milliseconds, 7 milliseconds. Okay, now let us let us take the same example. Let us see how a preemptive scheduling would have scheduled the processes. Now this time we will also consider the arrival time so that we can understand the preemptive SJF better. Okay, let's take up this example. Here you can see we have also considered the arrival time. Okay, process P1 arrives into the ready queue at t is equal to 0, P2 at t is equal to 1, and so on. And we have also taken the next CPU burst time here. Now let's try to write the Gantt chart which shows the scheduling decisions made by shortest job first scheduling algorithm, and I will tell you why it is preemptive. Now when you start at t is equal to 0, Which process is there in the ready queue? There is only one process in the ready queue, that is P1. So therefore there is no other choice but to give the CPU to this P1. And assume that this P1 has run for one time unit. Now this is when P2 is arriving into the ready queue. Okay, this is when P2 is arriving into the ready queue. What is the next CPU bus time of P2? It is 4. But how much time is left uh, for P1 or the next CPU bus time of P1? It has already completed one time unit, but 7 time units are left. This 7 is greater than 4, therefore P1 is preempted. This is what I mean by preemption. So now P1 is preempted, and which process is given CPU? That is this P2. Assume that the P2 runs for one time unit, that is at 2, at time t is equal to 2, P3 comes in. Now P2 would have run for one time unit and its remaining CPU bus time is 3, but the CPU bus time of P3 which arrives into the ready queue next is 9, so therefore there is no problem and P2 is allowed to continue on the CPU. At t is equal to 3, P4 comes in. By that time P2 would have run for um, 2 time units, and what is the remaining CPU bus time of P2? That is 2. Okay, what is the next CPU bus time of this P4? That is 3. So 2 is less than 3, therefore P2 is allowed to complete. So it will complete after 5 time units. Okay, now at t is equal to 5, now we have P1 completed one time unit, P2 is done, we have P3 with 9 time units, that is the next CPU bus time of P3 is 9 and the next CPU bus time of P4 is 3. So which one has to be selected? Now this P4 has got the shortest next CPU bus time, so therefore P4 is given the CPU, and from here onwards it looks like a non-preemptive scheduling algorithm because no other process is coming in after this. So therefore P4 runs till 8 time units. At time t is equal to 8, which one is this is done, which one is picked up for execution out of the remaining two processes? It is P1 because its next CPU bus time is 7, whereas the next CPU bus time of P3 is 9. So therefore this is picked up and P1 is given. P1 is allowed to run. Okay, P1 is allowed to run till t is equal to 15, and this is done. P1 is done. The only process which is remaining in the ready queue is P3. Now P3 is given CPU and it will run for 9 time units. So it is going to complete after 24 time units. So what's the total time taken by all these 4 processes to complete execution? 24 time units, which is same as the amount of time taken in case of non-preemptive. Now let's try to calculate the average waiting time. See, the calculation of waiting time here is little tricky, so you have to understand that carefully. Okay, what is the waiting time of P1? P1, though it gets CPU at 0, that is immediately after its arrival time, After one, it is taken out of the CPU and it is made to wait from here to here. So that means it is 8 minus 1, that is equal to 7 time units. What is the waiting time of P2? P2 comes at 1. Immediately it gets the CPU and it completes its execution. So therefore it is equal to 0. Now what is the waiting time of P3? P3 comes in at 2 and P3 gets CPU at 15. So therefore it waits for 13 time units. And what is the waiting time of P4? P4 gets CPU at 5, but it comes in at t is equal to 3. So therefore it is 5 minus 3, that is equal to 2. Hope you have understood this. Now let us calculate the average waiting time. So average waiting time is equal to 22 divided by 4, that is equal to 5.5, could be milliseconds or whatever is the time unit. So this is how we can calculate the average waiting time. Okay, now I calculated the finishing time. Finishing time for P1 is 15, P2 is 5, and so on. And how do we calculate the turnaround time? Finishing time minus the arrival time, that is equal to 15, or you can add the waiting time to the burst time, that is equal to 15. So this is how we can get the turnaround time and finishing time for this shortest job for scheduling. Now what is the biggest problem in case of shortest job scheduling? That is predicting the next CPU burst time when the process comes into the ready queue. Now there is a method proposed which is called as exponential average, taking the exponential average of previous CPU burst times and predicting the next CPU burst time of a process. So this exponential average can be found using this formula, where tau n plus 1 is the next predicted CPU burst value, Tn is the um, Tn is the previous actual CPU burst time, and tau n is the previous predicted CPU burst time. Okay, and alpha is called as the scaling factor or weightage, which varies from 0 to 1. In simple terms, you can take it this way. This Tn as the recent information that we get, and this tau n as the history. Okay, so now if you take the scaling factor alpha is equal to 0, then this CPU burst completely depends on the history. If you take alpha is equal to 1, in that case it completely depends on the recent CPU burst value. So in order to give equal weightage for recent CPU burst time and the history, normally the value of alpha is taken as 0.5 or it is taken as 1 by 2. So this is one of the approaches used to calculate the next CPU burst value. Though this works normally, SJF scheduling algorithm is called conceptual or hypothetical algorithm and not practically implementable. So that's the disadvantage of SJF algorithm. I have listed out advantage and disadvantages of shortest job first. scheduling algorithm. We have seen that we took one example, and we have seen after calculating the average waiting time, it came out very less for SJF compared to FCFS. Therefore, we can say that it minimizes the average waiting time. But the disadvantages are, it is not practical, as I told you. It is only hypothetical or conceptual, and it is very difficult to predict the next CPU bus time of a process. Here what may happen is, let us say now we have processes like this queued up for execution. Let's say this is a longest process, in the sense it has got a lengthier next CPU bus time. If P1, let us assume P1 is picked up for execution, and after this P1, P3 has got let's say less CPU bus time compared to this P2, so therefore P3 will be picked up. Now when P3 is running, let us assume that one more process P4 comes up, which has got the less CPU bus time than the P2. Then P2 will be kept in the ready queue only, and P4 is given the CPU. By the time P4 finishes, if some other process like P5 having less CPU bus time comes into the ready queue, P2 will stay in the ready queue only. So this is what is known as, now this P2 is starving. This is what is known as starvation. So this SJF results in starvation of this kind of process which has got longest CPU bus time. So this is what is about shortest job first scheduling algorithm. We will discuss about the next scheduling algorithm in the next lecture. Let me stop at this point of time, and if you have any queries or doubts, you can message me through the private chat. You click on my name, which you can see on the left side of the screen, and start the private chat. Thank you so much.